Hello, welcome to this video 4-5, and we are going to approximate values of a function using a tangent line. We're going to cover three big ideas from these notes. We'll go ahead and review how to write the equation of a line. That's very important, and especially a tangent line. And then we'll understand the concept of a function, understand the concept of a tangent line to a function. And then what we'll do with this is we will use the tangent lines to approximate a function value near the point of tangency, okay? And that's the main outcome of this lesson. Now, it's very important to remember that a tangent line is just a line. That is all it is. And in order to write the equation of a line, we need two things. What is it? Yes, a point and a slope. We need a point and a slope, and for our sakes and purposes it's going to be the derivative when we are looking at a function. So alright, here is just a recap on how to write the equation of a tangent line. So let f of x be a function. Now in order to write the equation of a tangent line to the function at x equals c, we must know two things. What's the point? Well, I'm going to take that x value. Sometimes you have to go ahead and plug it into the function. I'm going to plug it into f of x and go ahead and see what that y value is. Sometimes they give you the y value. It just kind of depends. That's going to be the point of where the tangent line touches the function. And then the second thing that we will need is we need slope. And that is just the derivative at that c value, or at that x value. Okay, so we'll take a derivative and then plug the x value into it. Now here's just a reminder of point slope form. And this is the function that I primarily use. Y minus y1 is equal to m times x minus x1. Or you can go ahead and see it in these terms right here. Y minus f of c is equal to f prime of c times x minus c. Okay, so let's go ahead and just kind of recap. How do I go ahead and write the equation of a tangent line? So let f of x equal 3 times e to the power of 2x plus 5. Write the equation of the tangent line to f of x at x equals 0. Okay, so the first thing that I need is a point. So I'm going to go ahead, I'm going to find my point. Now, they already gave us the x value, it's 0. Now, what I need is I need the y value. So that's going to be f of 0. So 3 times e to the power of 2 times 0. That's just going to be 3 times 1 plus 5, which gives us 8. So 0, 8, that's the point where the tangent line is touching the function. And now I just need slope. What is the slope of this tangent line? M is equal to. So what I need is I need f prime of x. I got to go ahead and differentiate my function. So 3 times e to the power of 2x is the derivative times the derivative of the power of e, which is 2. So 6e to the power of 2x. The derivative of 5 is 0, so we don't have that present. So there's f prime of x, and now again I just want this derivative evaluated at 0. So I can go ahead and plug this in. We have 6 times e to the power of 2 times 0, which just gives you 6. So there's my two things. I have my point, I have my slope, so I can go ahead and write the equation of my line. Y minus 8 is equal to 6 times x minus 0, or just 6x if you will. But this is equivalent. There is your tangent line. Let's go ahead and do the same thing, but in example number 2, the derivative of the function is given by already a derivative. I have a differential here, what we call a differential equation, and right there, this is the derivative. They say y is equal to k of t, so here's my function, k of t, and the derivative of y is equal to 1/4 y plus 5. It is known that k of 3 is equal to 19. Write the equation of the line tangent to k when t is equal to 3. Okay, so step 1, I need a point. Well, don't they give us a point here? And then this term, we have a t and then a y value. So I have 3, 19. There we go. And then I need a slope. I need slope. So usually I need a derivative. But in this case, they already gave us the derivative. They already gave it to us. dy dt is equal to 1/4 y plus 5. Well, our y value is 19 plus 5. So this is 1/4 of 24, which gives us 6. So our slope is 6. And there we go. We have all the things that we need. Y minus 19 is equal to 6 times x minus 3. And there's your function. All right, so why tangent lines? Why are we using tangent lines in this lesson to help us approximate or evaluate functions? Well, tangent lines can help us approximate values of a function when we cannot easily evaluate the function. Thus, this application would generally be in a non-calculator active situation to kind of help approximate values. Notice the function f of x and the tangent line t of x to the right. So here's f of x, here's the tangent function t of x. Now when x is equal to 5, the tangent line t of x has the same y value as f of x. So they are, t of x is tangent to f of x right here at x equals 5. Now, at values near 5, the tangent line t of x is near the graph of f of x. Aren't they really, really close here? Not so much down here, like at 2 and at 9, but right around 5, these values of t of x, that linear function, is really, really close to f of x. So this idea allows us to use that tangent line to approximate values near x equals 5. For example, t of 5.1, maybe say a value right here, is approximately the same as f of 5.1, which is maybe right here. Okay, and we can go ahead and see that. Now, we'll get into ideas later on, I believe in the next unit, about is this value an underestimation or an overestimation? That has to do with the curvature of the function. But here you can see t of x is kind of underneath f of x. So in this case, our approximation for t of x would be an underrepresentation of f of x. Again, that's a little sneak peek, more on that to come in upcoming lessons. All right, so let's go ahead and look at applications of this, and we'll do this through the lens of a tabular problem, where here I have a given x values, I have function values, and then derivatives at those x values. So they say in example 3, the functions of f and g are differentiable with selected values of f, g, f prime, and g prime given above. Let h of x be equal to f of g of x. So I have a function defined as a composite function. And we're going to go ahead and they say write the equation of the line tangent to h of x at x equals 4. Okay, so I need two things. My approach to these problems never changes. Okay, I know my x value is 4. Now what's the y value? Well, I have to evaluate my function, h of 4. So I have f of g of 4. And I'm going to go ahead and just plug in 4. So I'll use my table. Okay, when x is equal to 4, it looks like g is 5. And then now I need f of 5. So at 5, f is negative 9. So there is my y value. There's x, there's y. Okay, 2, I need slope. I need to know what the slope is at that x value. So I need h prime of 4. Well, I have to go ahead and I have to take a derivative first of h of x. So before I evaluate at 4, I'll just keep this general. I'll say what is h prime of x. So derivative of the outside, f prime of g of x times the derivative of the inside, which is g prime of x. Okay, and we'll go ahead and calculate this. H prime at 4 gives us f prime of g of 4 times g prime of 4. Okay, so using our table of values here, it looks like f prime of, we already found out that g of 4 was 5, so I can plug that in using our table, times g prime of 4. That's going to be -2. Okay, and then substituting f prime of 5. F prime of 5, here's 5. F prime is 3. So we have 3 times -2, which is -6. Okay, so this is equal to -6. All right, I have my point and I have my slope. So therefore, my equation of my line is y plus 9, not 6. That's the slope. Is equal to -6 x plus minus 4. X minus 4. So there's our equation. Okay, here is the new learning. Here's where part B comes into play. Use the tangent line from part A to approximate h of 4.1. So again, this is my tangent line. It's not my actual function, but I can use this to approximate values. Now these problems, they always give you an x value or an input value here really close to your tangent line x value. So notice how that's at 4. Okay, so if I'm going to go ahead and do this, I'm going to say h of 4.1 is approximately, and I'm going to use my function here. So we have, well, I'm going to do it this way. -6 times 4.1, I'm just plugging in 4.1, minus 4, minus 9, minus 9. All I did here was I moved that 9 back to this backside, right there. Okay, so there is my function value. That's approximately that. And I'm going to go ahead and now calculate this. So if you do this correctly, this will be a really simple, small, easy value to calculate. So that's 0.1. So we have -0.6 minus 9, which is equal to -9.6. Okay, so h of 4.1 is approximately -9.6. Example number 4. And that's it. It's that easy. It's that easy. Example 4. Let y equal f of x be a function with the derivative of y with respect to x being equal to 3x over y plus 4 squared and containing the point 1, -5. Write an equation for the line tangent to the graph at y equals f of x at x equals 1. Use your equation to approximate f of 0.8. So notice two distinct tasks that they have given us in this problem. The first thing, I need the equation of a line tangent to y equals f of x at x equals 1. So what do I need? Well, I need a point. I'm going to give myself some room on this because this is kind of both parts in one. So my point is 1, and I need a y value. Hey, they gave that to us. That was -5. Step 2, I need a slope. M is equal to, well, I need a derivative. Hey, they gave us the derivative on this. dy dx. This is the derivative. So I'm going to go ahead and plug this in. So 3 times 1 is equal to -5 plus 4 quantity squared. That gives us 3 over, it looks like -1 squared would be 1. So 3. That's our slope. Okay? So now I'm going to go ahead and I'm going to do the first test. Y plus 5 is equal to 3 times x minus 1. And if I want to put this in an equation that's ready to go ahead and calculate, it is 3 times x minus 1 minus 5. Now notice I don't distribute that 3x because the way these problems again work out, I'm going to plug in a value that's really close to my x1. So let's go ahead. They want us to approximate f of 0.8. Okay, so that is approximately 3 times 0.8 minus 1 minus 5. And this is going to be equal to 3 times -0.2 minus 5. So we get -0.6 minus 5, which is equal to 5.6. Now both of these answers have been negative. It won't always work out that way, but that's kind of just what we've gotten so far. Okay, very, very simple, very, very straightforward. All right, last example that I have for you. On Thanksgiving, a delicious pumpkin pie removed from the oven has a temperature of 175 degrees Fahrenheit. The temperature of the pie at time t minutes can be modeled by the function p, where the derivative of p, this is all bouncing around, where the derivative of p with respect to time is negative 1/50 times p minus 25. Use the tangent line to p at t equals 0 to approximate the temperature of the pie 4 minutes after being removed from the oven. Okay? So, step 1, I need a tangent line. Okay? I need a point. Number 1, what is the point? Well, they tell me at time t equals 0, and I need to know what is the temperature of the pie at 0. What is the temperature? Well, they said when we take it out of the oven, that pie is 175 degrees Fahrenheit. Now what I need is I need the slope. So what is the slope? Well, I'm going to go ahead and I'm going to use the derivative that they give us. So the derivative of p with respect to time is equal to negative 1/50 times p minus 25. Now remember, p, that's the temperature of the pie. That's the temperature of the pie. It's not time. It's not t. So I'm going to plug in here 175. That is the point in question, right? I'm using this point here to evaluate the derivative. So 175 minus 25, and this gives us negative 150/50. So negative 3 is our slope. Okay? So that means, right, the temperature is dropping 3 degrees at every minute initially, okay? So our equation, our tangent line equation, y minus 175 is equal to negative 3x minus 0. And I'm going to keep it in this format again, but I'm just going to move that 175 over to the other side so I can go ahead and easily approximate. Now they want the approximate temperature 4 minutes after being removed. So this is P of 4. Okay, P of 4 is approximately negative 3 times 4 minus 0 plus 175. And if we go ahead and calculate this, negative 12 plus 175, this is going to give us 163 degrees Fahrenheit. All right, there you have it. In this video, we went ahead and we reviewed how to make the equation of a line, and specifically a tangent line for a given function. We reviewed the concept of a tangent line to a function, what that kind of looks like, and how we can use it. And then step 3, we use the tangent lines to approximate a function. Give me a thumbs up, like this video, give me some support, subscribe for more awesome math videos. Catch you in the next one.